Hello, welcome to the lecture 14 of the course Transportation Network Analysis. So, in the last class we were discussing about iterated tour partitioning algorithm for solving the CVRP with equal demands. So, we will be continuing that discussion today also. So, we had seen an example of this iterated tour partitioning algorithm. So, now let us formally see a few things here. So, this algorithm starts at the depot node and it follows the tour that is given. So, remember that in this ITP algorithm we have a tour that is initially given. So, we start from this depot node in this tour and we follow this tour in an arbitrary orientation, and the customers and the depot node are numbered x0, x1, xn, where x0 is the depot node. Okay. And then what we do is that we partition the path from x1 to xn into, this is the ceiling function of n by q, or the ceiling of n by q plus 1 disjoint segment, such that each contains no more than q customers and connect the endpoints of each segment to the depot node. Okay. So, if you remember in the last example that we had seen, so we had obtained two solutions from that. One was this x0 node, that was the depot node, and then we had these 6 customer nodes that were there. This was x1, this was x2, x3, x4, x5 and x6. Okay. So, in the first case we had this solution where this segment was only consisting of x1, the second segment only consisting of x2 and x3, the third segment was consisting only of x4 and x5, and the last segment was consisting only of x6. Okay. So, here n was equal to 6, okay, because there are 6 customers here. Q was given to be equal to 2. Okay. So, n by q is equal to 3. Okay. So, and ceiling of 3, so 6 by 2, and ceiling of that is again 3. Okay. So, this number in that example is 3 here, and this will be 4. So, this was the first solution that we had seen. So, here you can see that actually the number of segments are 4, one only going to the customer x1, the other is the one which is going to customers x2, x3, the third one is the one going to x4, x5, and the last one is the one going to x6. So, that is why here you can see that the number of disjoint segments that we will be obtaining is either the ceiling value of n by q or ceiling value of n by q plus 1. Okay. So, therefore, here we are obtaining 4. Okay. So, that is why we have this thing written in the bracket that ceiling value of n by q plus 1 solutions also you can obtain. In the second solution that we had 3 segments only, the first one was visiting x1 and x2, then the second one was visiting x3 and x4, and the last segment was visiting x5 and x6. Okay. So, here we had a total of 3 segments, and that is this thing. Okay. So, that is why you can see that why we have written this ceiling value of n by q, you will either obtain that many disjoint segments or the ceiling value of n by q plus 1. Okay. So, the first segment contains only customer x1, okay, in the first solution that we are generating, and all the other segments contain exactly q customers except maybe the last one. And this was also the case in the first solution that we obtained, because in that example the first segment only contained the customer x1, the next 2 segments contained 2 customers x2, x3, and then x4, x5, and the last segment only contained 1 customer, because we just had 6 total customers there. So, this gives us the first feasible solution to this problem, and then we repeat this above construction by shifting the endpoints of all but the first and the last segments up by 1 position in the direction of the orientation. Okay. So, now in the next solution that we obtained, we had also added x2 to the first segment. Okay. Now, the next segment, then we put together the customers x3, x4, and then x5, x6. So, in that way we generate the next solution. Okay. In that example, it is not possible to generate further solutions because q is equal to 2. So, every segment cannot have more than 2 customers. So, this procedure is repeated q minus 1 times, producing a total of q different solutions. Okay. So, q was equal to 2 in that example. So, we saw that there were 2 solutions that we finally obtained, and then we choose the best of the set of q solutions that are generated. So, out of the 2 solutions that were generated, we find that solution that has the least length of all of the tours. Okay. Now, given a feasible TSP tour, the running time of ITP algorithm is of the order nq. Okay. Why it is nq? Because first we will be generating q such solutions. Okay. And each such solution we will be having at most n segments, and that is why it will be at most of the order nq operations that we will be requiring. Okay. Okay. So, one thing to think about is that how good solution this ITP algorithm will depend upon how good your initial solution of TSP tour you have. Okay. Because all of the solutions that you generate depends upon this initial TSP tour, because you are only segmenting this tour in a particular way every time. Okay. But what remains constant is that the order of the nodes that comes. Okay. So, for example, when you specify this tour, then you already specify that after this x0 node, one goes to x1 node, then x2, x3 and x4, xn, and then come back to the depot node. So, this order has now been fixed by the tour that you chose in the beginning. So, now how you divide this, like how you will club together these different customers in this tour, is the only thing that you can do. Okay. And that will generate different solutions. So, therefore, the quality of the initial tour that you select is important here. So, let L rho be the total length of all the segments as obtained using this, using the initial tour from TSP algorithm that has an approximation ratio rho. Okay. And let L star be the total length of an optimal solution. Okay. So, here it is saying that suppose L rho is the total length of the segments that you obtain if suppose you start with a tour of TSP algorithm that has an approximation ratio of rho. Okay. That is, for example, you know that for the TSP problem of the graph that is given to you, the tour that is generated is suppose generated by an algorithm that gives you suppose approximation ratio of 2. So, you know that this TSP tour cannot be larger than twice the optimal TSP tour. Okay. So, that 2 factor is the approximation ratio for that TSP algorithm. So, let L rho be the total length of the tours that is obtained by this ITP algorithm if you suppose start with an initial tour that has been obtained by an algorithm with approximation ratio rho. Okay. And let L star be the total length of the optimal solution. So, L star is the value of the optimal solution that you have in this vehicle routing problem. So, it will be the length of all of the tours in the optimal solution. So, then this result holds that L rho by L star is less than or equal to 1 plus 1 minus 1 by q times rho here. Okay. So, again this holds for all the instances of this problem that we are discussing. Okay. And of course, it has a proof behind it, but we will not be going into that for the sake of time and for the scope of the course that we have to cover here. So, for example, if the initial tour that we start with in this ITP algorithm is suppose obtained by using this MST based algorithm that we had seen for solving the traveling salesman problem. So, there the approximation ratio was rho. Okay. So, then what we can guarantee is that this length of the iterative tour partitioning which is L rho that is obtained will be less than or equal to L star times this ratio here. Okay. So, now instead of rho we have put 2 here, and depending upon what is the q that we have in the vehicle routing problem, this ratio will get determined. Okay. So, you can see that if rho is larger, that is this approximation ratio is larger, that is the guarantee that you have between the value that you obtain from the traveling salesman algorithm versus the optimal traveling salesman tour, if that guarantee is loose, that is rho is large, then automatically the guarantee that you will be getting, that is this approximation ratio here in this iterated tour partitioning algorithm, will also be looser, that is this will also increase, that is the largest value this L rho can take will be L star times this ratio, okay, and this will increase if rho will increase, okay. Okay. Now we will be considering another version of this capacitated vehicle routing problem, which we call capacitated vehicle routing problem with unequal demands here. In short, it is called UCVRP. So, here U is for unequal. So, the difference with the ECVRP that we had seen is that each customer I now has a demand WI of the products it is asking, and here the constraint is that the total amount that is delivered by a single vehicle cannot exceed Q, and in this version the demand of a customer cannot be split. This is the main thing, okay, over several vehicles. So, here this is that case where every customer is saying that if I am asking for suppose WI units of a product, so I do not want multiple delivery guys coming to me and giving me the total amount of WI, okay, or multiple vehicles coming to me. I want that a single vehicle or single person comes and gives me that total WI units of that product, okay. So, in this case we do not allow the demand to get split among multiple vehicles, okay, and this splitting may be undesirable due to customer service and so on, because it may not be convenient for a person to keep receiving, say if he had asked for 10 units of a product, so then one vehicle gives him 1 unit, then the other one gives him 3 units, then 1 and so on, I mean, okay. So, this is very undesirable and inconvenient situation. So, in this savings algorithm which has been proposed by Clark and Wright in 1964, we do not allow the splitting of demand to happen. So, this is used to solve the UCVRP problem, and this algorithm has been used by various commercial vehicle routing packages. But just to emphasize that why we first started to discuss that problem ECVRP and then we shifted to UCVRP, even though UCVRP seems more practical because no one would want to have getting multiple deliveries of some product and everyone would prefer to have a single delivery, is because ECVRP is a simpler problem than UCVRP, and therefore once we get insights to solve that simple problem, then only we can expect that we will be in a better situation to solve a more complex problem. So, that is why we discussed the simpler version of the problem, and now we are focusing on UCVRP, okay. That is the same reason that we first focused on the traveling salesman problem and then we discussed the more complex problem, which is the vehicle routing problem, okay. So, this savings algorithm is also one of the earliest designed algorithms in the vehicle routing problem, and it is one of the most widely known. So, the idea of the savings algorithm is as follows. Suppose that we initially assign a single vehicle to each demand point, okay. So, now this savings algorithm is in a way kind of opposite to what ITP algorithm was doing for ECVRP. So, in ITP algorithm we had a single tour and then we were partitioning it to various segments, so that every segment corresponds to a single vehicle. Now, we are first assigning a single vehicle to each demand point here, okay, and then in a particular way we will be clubbing together these different demand points or customers, so that they can be served by single vehicles. Now, how to do that clubbing or that agglomeration is specified by this savings algorithm. So, suppose the total distance that is travelled by a vehicle that visits demand point I is 2 di, where di is the distance from depot to the demand point I. Okay, so, we are assuming that suppose this is the depot node here and this is a point I here, okay. Let us assume that the distance to go from depot node to point I is the same to go from point I to depot node, okay. So, okay, so this total distance that will be covered by a single vehicle, which starts from this depot node and it goes to point I and then comes back. So, this will be equal to 2 di. Okay. So, the total distance that is travelled in this initial solution, where every demand point is served by a single vehicle, or every customer is served by a single vehicle. So, that will be equal to twice the summation of di, where I goes from 1 to n, where n is the number of demand points or the customer points. Okay. So, now just to again emphasize that now here every demand point or customer point need not have one unit of demand that they are asking for. Okay. Everyone can have different demand values. So, if we now combine the two routes, say we serve the two customers I and j on a single trip with this, that is with the same vehicle, the total distance that will be covered or travelled by this vehicle will be equal to di plus dij plus dj, where dij is the distance between points I and j. Okay. So, suppose you have a point j also. Okay. So, we are now going to this depot node, but now we are not coming back directly. From depot node we are going to point I, and then from point I we are going to point j, and then we are coming back here. Okay. So, this total distance that will be travelled will be first from depot node to the point I, which is di, then from I to j dij, and then from finally from point j to depot node we will be travelling dj. Okay. Okay. So, in this case we have now clubbed together these two points or customers with on a single trip. Okay. So, therefore, when we do that, the savings that is obtained from combining these demand points I and j, let us represent it by Sij. So, this is equal to, see, this was the total distance that was being travelled when we had separate vehicles travelling to both of these 2 points I and j. Okay. So, the first vehicle that goes to this point I and then comes back again, so that will travel this distance 2 di. Similarly, the second vehicle which separately goes to this point I and then comes back, that will travel 2 dj. Okay. So, this is the total distance that will be travelled by the two vehicles when each of them is separately serving every point, and then this is the distance that is travelled when a single vehicle goes to point I and then it goes to point j and then comes back to the depot node. Okay. So, therefore, this is equal to di plus dj minus dij. Okay. So, this is the saving that is obtained. Okay, because this length is hopefully smaller than this one. Okay. So, now larger the savings that we get for this pair of points or customers I and j, the more desirable it is to combine these demand points I and j. Okay. So, initially in this solution, as you mentioned that a single vehicle is visiting every point, now we have to decide how should we club together these different points that we have. Okay. And that decision is being taken by this savings that we have here, saving function. So, based on this idea, Clark and Wright had suggested this following algorithm. So, here they first start with a solution where each customer is visited by a separate vehicle. Okay. And then we calculate these savings Sij equal to, this is the distance from the depot node to the point I d0 I plus dj0, which is the distance from point j to depot node minus dij. Okay, for all pair of customers I and j. And then we sort these savings in non-increasing order here. Why we are saying non-increasing? Because it can happen that for two pair of nodes the savings can be equal. So, then we can put together these savings of these two pairs in any order. So, that is why it is non-increasing rather than decreasing. And then we find the first feasible arc ij in the savings list, where now these conditions are important. First thing is that I and j are on different routes. Both I and j are either the first or the last visited on their respective routes. The sum of demands of routes I and j is no more than q, and if all of these conditions are satisfied, then we add this arc ij. Okay. We will refer to arc, link, edge interchangeably in this course. So, if we add this arc ij to the current solution and we delete these arc 0i and j0 here, okay, and we also then delete this arc ij from the savings list, and then we keep repeating this step 4 until no more arcs satisfy the conditions. Okay. So, we can see an example to understand this algorithm here, but remember that these 3 conditions are important in step 4, that is when we are combining 2 points ij while using the savings list, the ij should be on different routes. Now, route means that it is the set of points which is getting covered by a single vehicle, and both ing should be either be the last or the first visited in the respective routes, and when we do this clubbing, it should be that the sum of the demands of routes ing should not be more than q. Okay. So, let us take a look at an example here. Suppose we have this depot node here D, which let us represent it by O here, and then we have suppose 5 points here represented by A, B, C, D and E. Okay. So, in the initial solution, each segment will only consist of a single demand point or a customer. So, every vehicle will be visiting a single demand point. So, here we have 5 points. So, therefore, we will be having 5 vehicles that will be visiting them. And after that, suppose we have a savings list that is given to us. Okay. So, suppose the savings list is like this, that suppose DE has the highest savings, then suppose BC has the next highest savings, then suppose AC has the next highest saving, and then suppose CD and so on. Okay. So, the number of these savings will be equal to the number of pairs that we have here. Okay. So, there are 5 nodes here. So, we will be having these different combinations of these 5 nodes here. Okay. So, since DE has the highest saving here, so we will be clubbing together these 2 points D and E here first. So, let us suppose that Q is equal to say 15, and these different demand points are asking for these many units here. So, point A is asking for 5 units, the point B is asking for 2 units, point C is asking for 4 units, point D is asking for 6 units, and point E is asking for 7 units. Okay. So, before we decide to say club together D and E here on a single trip, let us see that whether these conditions are satisfied. First of all, D and E are on separate routes because they are getting visited by separate vehicles, that is satisfied, and then D and E are also, they are the first or the last in respective routes because there are single vehicles that are visiting them. And if you club together these 2 points D and E, which is 6 plus 7, you will get 13, which is still less than 15. So, that is fine. So, we can then club together D and E. Okay. So, D and E we will club together. Okay. And then we will be removing these 2 edges here. Okay. And we will also be removing this D from the savings list. Okay. Now, suppose BC has the second highest savings here. Okay. So, we can also again club together B and C, because B and C are on separate routes. First of all, they are both of getting visited on separate vehicles, and since they are single points in their vehicles, so they are definitely the first and last, and adding 2 to 4 is again less than 15. So, we can add these 2 also here. So, we will remove these. Okay. And we will remove this also. Okay. Similarly, we have next AC. So, again we can add them together because A and C are on separate routes, they are in the end, and adding 5 plus 2 plus 4 will not exceed 15. So, we can connect A and C also together here. So, we will be removing this part, and we will be also be removing this part here, and we will be connecting this here, and we will be also erasing this. Okay. Okay. Now, we remove this AC also. Now, CD is the next in the saving order, but we cannot connect them because this, you can see that node C here is in the middle of its tower, whereas D here is not. Okay. So, this is in the end, but C is in the middle. So, we cannot connect CD. So, that is why we will stop here. Okay. So, with this we will be ending this discussion. Thank you.